And I think we are live. Cool. All right. So I copy and paste this from the lecture the other day. We'll finish this one up. But you get the bit here when we're looking for the volumes that we have higher temperature plus the lower temperature one combined. Did I do the example where I didn't do it as a modified system? I don't think I did.
I think you said you're going to finish it.
All right, let me finish this one. Maybe we'll go back and hit the one that's unmodified, because believe it or not, it gives you, unmodified, it gives you a horrible answer and doesn't even come close. So let's do, where are we at here? Okay, so we got, we need to put numbers in. Yes, okay, cool. We are, no, get out of there, don't want. All right, so we are looking at
Is the answer you have posted for the unmodified one? The answer 21?
I think it was for the, the unmodified one.
Okay.
Yeah, that's what I did. That's right. We'll go through that so you can see how it works. So VT is equal to the higher temperature, higher volume, and that's in the boiler, so that's 15 gallons. And you're going to multiply that times the density of the cold water coming in, and that'll be 62.36 pounds per cubic feet, divided by the high of the boiler, which will put it at 60.06 pounds per cubic feet. And then, we got to minus all that by 1. And we're going to add the volume of the low, which is 200 gallons. Right, that's what that was. 200 gallons of water in a radiant floor system, yep. Times the well, that's a stupid way to write that example. DC cold, 62.36 pounds per cubic feet, because that didn't change, divided by, let's get that parentheses a little bigger, divided by 61.84 pounds per cubic feet. And my question earlier, just so you know what I was questioning, I was looking at the solution the book did, and they actually wrote this as 62 plus 36 to the density. It's like, no, you screwed that up. There's supposed to be a decimal there. Okay. And that is all bracketed, so that'll give Dylan a challenge with the calculator. Times
real quick.
30.
Why is it 60.06 to 61.94? Is it like when the higher temp, the density goes up? Higher density goes down?
Higher temperature, density decreases. Lower temperature, density increases. Remind me, and I'll draw you a nice diagram for that. Because I also went out and I did some homework for you guys, and I went out to Engineering Toolbox and got you a table for it. But I was also reading through Siegenthaler's book here, and he does, let's use an equation. So I'll give you the equation, but the reality is I would go look it up. No one actually uses the equation. It's just, I'd say it's insane, but it's has no real reason in life. if you got a table. Okay, so recap this. We took the boiler. So all of this here is the boiler water. Okay. All of this is the radiant floor. Or if you had, you could use this on a, okay, I want to say this. So you got a hydronic boiler that feeds a primary loop. So that's this primary loop. Then the secondary loop is something that has a lower temperature. So there are mixing valves that will lower the water to, say, 140, but your boiler only operates at 180. So that changes the water density on this. So it's another way to look at this is primary loop and secondary loop. So that you keep those things straight. And the answer to this one becomes 7.3 gallons. So we're going to have to go find it. It would be nice if you could find an 8-gallon one, but you're probably going to have to go get a 10-gallon one. Okay. But you see the answer I did for the non-modified one up here, which is the way we did the very first one, is 21.6. So you'd really have an extremely oversized system only because of the it's not accounting for the lower density of the water than the other piece. So cool. All right, Deb, you asked the question about density, and there is a formula for that. Where did I see that? And there's a graph. Let me go get a book and tell me what page it's in. Density. Page 141. Okay, so this is the and let me do something else here. Let's put some grid lines in this one. Make that a little easier to draw and see.
Can you scroll up just that last part? I just spent the last 2 minutes looking for paper because I forgot my notebook at school, and I'm just thank you.
Yep.
You already knows?
Yeah, I'm a scholar. No.
Well, you know he's going to have to explain it to Dylan. Nope, Dylan's in here.
Yeah,
I'm not taking any notes, but I'm here.
I'm not taking any notes, but I'm here.
Yeah, I'm driving back to school right now.
You are?
Yeah, I was home I had to work on Saturday, so
How are the roads?
they're not bad. Last night I was trying to come home and I had to turn around because it was nasty, but they're good today.
Okay, so there's that. And if we do density 58, 0, I'm going to do them by ones, 59, 60, 61. Tables you see for this are a little more precise, but since I'm duplicating all this, make that look like a 4. Okay. So our curve for this looks something like this. So we're 62.4, and depending on where we are, 49. So we're going to start, I'm going to do that in red. We're going to start right there. And as we end this thing, we're going to end about 59 over here at 250. Okay. But then literally it plots something like this. So it's a downward curve. And, oh, what the hell? You might as well have the equation. This is row. And pounds per cubic feet. If you're going to do a graph, do it right. The equation for this thing looks like this. So density or rho, depending on which one you like, is equal to 62.56 plus 3.413 times 10 to the negative fourth multiplied times the temperature minus 6.255 times 10 to the negative fifth, and temperature squared. Okay, so it's it's a curve that actually just changes with the square root of the temperature. Or not the square root, the square of the temperature. So we got a polynomial equation here for this curve. All right. So it is what it is. Now, the cool bit, and I looked this up someplace for you. Oh, yeah, I know. I put it in the homework assignment. Hold on 30 seconds. Let me see if I can find this link I gave you, because we can definitely go use this. You're in the wrong screen. Get over here. Alright, I looked this up earlier today. Water temperature differential. And if you go to here and go to visit, I don't know if I've ever taken you guys out to Engineering Toolbox, have I? So if you come in, hold on, yeah, if I come in here and it gives you, so Engineer's Toolbox gives you a lot of theory background on stuff. You got to work your way halfway down, but there is a calculator here, but this is the curve I was just drawing for you basically in this one. Okay. Density in pounds per cubic feet, bang, and away you go. Okay. But it's this piece right here. So if we want 170 degree water, and I come down here and tell it's Fahrenheit, calculate, it gives me every known number related to that and every unit that it possibly could come out in. So what you're looking for is 60.793 pounds per cubic feet, and bing bang, you're done. So why go use that lovely equation when you can just find this little bit? That makes sense?
I'm glad that it's more than just American units.
Why it's, well, but it's kilograms per meters cubed. So think about it. 900. So water density at 4 degrees C would be 1,000 kilograms per meters cubed. So it's still going down in density as the temperature rises. So in some place, did you guys learn that?
I don't know why I'm not worried about that, but I needed to know that, and I wish I knew it sooner. That it's inversely proportional when it comes to that.
Okay. Well,
life would be easy.
So the colder the water gets, the denser it gets. But water is also one of those funny set of molecules that at 4 degrees C or 37 degrees Fahrenheit, I think somewhere in there, it's the densest it's going to get. And as it goes towards freezing, it becomes less dense again. So that's why it floats and why ice floats on lakes and rivers and all that sort of stuff. So cool. Everybody good with that? It's kind of and you're going to want that screen too, because I did put that in the homework I gave you. Stop it. Thank you. So anyways, you can use the equation or just look it up. I gave up doing a lot of math if you didn't have to. That's just one of the things. Cool. What was I going to go with next? That wasn't the next topic. That was just. Oh, I know what it was. So one of the other things we got to talk about with this is, you remember you needed the volume inside the pipe, and that was this VS up here, volume of the system. So when you don't have a real nice way of doing this, you could create it by hand. But here's some numbers. So if we're using copper, and I should label this thing as volume factor 4 tubing. All right, and we'll do PEX because that's another one we need to play with. And then, believe it or not, PEX, aluminum PEX, is another type of PEX that we need to use for radiant floor systems. But you're going to get these in gallons per feet, and they're all gallons per feet, yes. Okay, so I'm going to do half inch up to like inch and a half, but we're not going to do every number of the planet. So let's do half inch. You are looking at 0.01319 for the PEX. You're looking at 0.009609, and then for the aluminum core, you're looking at 0.01038. Okay, and as long as we're here, so half inch copper has a larger inside diameter than does PEX, and so PEX fittings are a little harder not a little harder to get. They're a little harder to size and get the same volume that you would out of copper. So when you do a radiant floor, there's a whole bunch of different numbers you got to use there. So next is 3/4 inch. This is 0.02685. And then normal PEX is 0.01894. And the aluminum core PEX is 0.02654. Oh, and I should explain the difference between PEX and the PEX aluminum PEX. So normal PEX is polyethylene extruded molecules, and then the PEX aluminum PEX is poly what did I just call it? Poly E is polymer chain here, and then has an aluminum core with another polymer chain on the inside. And what happens is PEX normally allows oxygen to go in and out of the pipe because the molecule chains are larger than the oxygen molecule but smaller than the water molecules. So in order to stop that, we add an aluminum core, which also helps with heat transfer and that sort of stuff. All right, PEX, polyethylene. Thank you. Polyethylene cross-linked is the X. Let's write that down so we don't forget it. Poly. And that is PEX. Okay. And the X stands for cross-linked, because literally what you get is you got a molecule like that and you got a molecule like that, and it forms a cross-linked molecule here that just keeps going on and on and on until it forms a pipe. But then we add an aluminum core in the center of it, and we let the cross-links happen out here and inside this, and bing bang, we're good. All right. So anyways, that's the definition of those two things. 1 inch, we're looking at 0.0454. 1 inch PEX is 0.03128. Does not look like an 8. That's an 8. And then the 1 inch aluminum is 0.04351. And normally we don't make anything larger when it comes to the PEX, aluminum PEX. But I'll go do 1.25 inches here so that you have this number. 0.06804, and then it is 0.04668. Okay. And then 1.5 inch copper is 0.09505, and that is 0.65164 PEX. Okay, and there is no sizes out there for that. So normally we don't do anything much larger than 1 inch for radiant floor systems, and everything else is, if you got to get larger to get water to a zone for radiant floor, you run copper over to it and then switch over to PEX. PEX allows us to make the range of things to move around. Okay. All right. Let's see how I want to do this next bit. Okay. So that being done, let's draw this diagram. So we got a boiler. And this is going to have 12 gallons in it. Okay. And we come up, we come over, we got an air scoop, and we got an expansion tank. All right. Then we got off this, the makeup water. And I know that's a really crappy valve. Okay, that's makeup water. And then we got a backflow preventer, which looks like this. And that bumps into something here. No, that bumps in the wrong way. Let's do it this way. That has a bump there, so it can't backflow to it. And then we got just a regular shutoff valve. Okay. All right. From that, we go over, and we're going to get our first zone. We're going to put some sort of emitter in here. We're coming out. We're going to get the next zone. We're coming out. It's going down that way. I'm doing 3 of these. Okay. If I do this right, I can use the same example to tie in the next conversation, which is all the fun things that go with systems. So we can have coming back around here, down. Drop a system there, and we're going to drop, oops, don't need that there, I need this here. We got this, we got one more, get it out of there. You're not watching this while you're driving, are you, Dylan?
No, I'm just listening to it talk.
Okay. All right. So here's a fun thing. So literally we can do goofy things like this. So put 55 feet, 1.25 copper here, and then we'll change it over to 45 feet of 1 inch copper here. We can then bring this one down to 25 feet of 1/2 inch copper here. We can increase this one so it's 35 feet of 3/4 inch copper. And then we can have this come back to it's 1 inch down to here. We'll pick this up as what are feet first. We'll make this 35 feet 3/4 inch copper. So literally we'll do it like this. Let's do this. I'll make this big and bold. We'll fatten that up. Then we're gonna do here, and we'll go here and around to here, and then we'll thin this out until we get over to here, and then we can switch it to this will be 3/4 inch or 1/2 inch. Then we'll make this 1/2 inch up, and we'll do 3/4 here, and then we'll get back to someplace right about here, up, back as the 1 inch or 1.25 inch, and then we got 3/4 through there. Okay, so you can just see a visual color now of it. But this piece here, this will be 70 feet. 70 feet of 1.25 inch copper. So literally you're going to have to take and use this set of data points up here to find parts and pieces of this. That makes sense?
Yeah.
Okay. So literally it comes out to 55 times the let me write that whole thing out so you can see it. Might as well do what it's worth doing if you're going to do it right. So the volume of the pipe will be 55 plus 70, and that'll take care of our 1.25 inch, and that number is 0.06804 from the table I just created you. All right, and then we're going to do plus 45 plus the 40 feet. Okay. And we're multiplying that now on 0.0454 because that's the 3/4 inch, or no, the 1 inch. Change 1 inch in here someplace else and then write it down. Oh, it's 1 inch in here, so it's 40 feet at 1 inch copper right through here. Okay. All right, so then we get that, and then we're looking at plus 35 feet. Again, we got plus 35 feet. And that's multiplied times 0.02685. Okay. Plus 25 feet plus 25 feet times 0.01319, and when you get all done, you wind up with 14.9 gallons in here. Okay, so that's the answer. Now, the other bit with this is we're working around this thing. So I had 55 feet of 1 inch, or 1.25 inches. I had 70. It's a good idea when you're designing your systems to try and keep those similar to each other, because at some point in the line you're going to have a balance flow issue, and you remember you want it to come back to the boiler and have it go through the circulator. I didn't draw the circulator in here, did I? Okay, so we got a pump up here. So that's our pump.
A quick question. Is it an equation? I see the measurements you did and where the table come from, but how did you get like the 55 plus 70? Like, did you post it in the equation?
No, it's not really an equation. It's just the logic behind it, Deb.
Oh, okay.
It's
I'm not taking notes, so I'm just trying
yeah.
to pay attention.
No, it's fine. So it's a good question. So I looked at, I got 55 feet coming from the boiler over to the first distribution point, and then the other one is from the boiler back to the second distribution point. Now I'm using the example out of the textbook here, but this is a point of, that's what you're getting. So that first one is literally, if I draw it, let's do some of the color I haven't used here. Let's do green. So if I take this flow, it's there, and this one, it's there. And then the 45 was this one here, and then the other 40 was this one there. So any place I had 1 inch pipe, I'm kind of adding it up. So if you think about this, this was all 1 point. You can't read that. This was 1.25 inches pipe. This was all 1 inch pipe. This one was half inch. 25. No, this is half inch pipe over here. This was 3/4. That makes sense?
Yeah, it does.
Okay.
That does make sense.
So you're really just using that to multiply it. Ideally, if everything was 3/4 inch, you just take 3/4 times the total number of feet, and you'd get that number. And that comes back out of this table that I gave you up here for some of these numbers. All right. And that table is more.
It's just a lesson how much I forgot last semester. But yeah, we did similar things last semester, so I get it. Thank you.
All right. So cool. That's how you get that. Now the other bit is there's software out there to do all this. It's just a matter, again, if you're going to use the software, you want to know it's doing it right. So you need to do at least some check to see if some of the numbers are coming out in the right direction. All right, how are we doing on time? Here we are. We got 10 minutes. Okay, so I said this morning we'd have a little discussion about what did I talk about? Primary and secondary loops. So back to block. We get a boiler and we come up and we got all the paraphernalia and an expansion tank. We got a pump with all its valves. We got makeup water and all that stuff in here. That's not a good valve. Okay, that's really a crappy circle too. Anything worth doing is worth doing right. Okay, so we come out of that circulator and we come back down and we come back into the boiler. Okay, so this will all be your primary loop. Okay, so ideally, all things the boiler's doing, it's just making hot water for itself, basically, until you branch onto it with some closed coupled T's. Okay, then you're taking off and you're heading out to a zone, and that zone could be stuff that looks like this, and I'm going to use this squiggle resistance kind of thing for parallel circuits. Come back out, it comes back in. Okay, I could do another one down here that takes off, and another one here takes off, and what this one's going to do is I will come out, up, and I'll do this. Okay. No, I don't want to do that. That's going to look like the same thing. I want this is a direct return up here. Okay, so water flows here and up. The water flows there and out, and then it returns back that way. So what I want to do is create a system that looks like this here. And this is going to go there. This will come over to here. No, it's not where it's jumping. It's going to do this. It's going to jump over that and then to here. Okay? And then this one, sure, when I want you to draw a straight line, you won't do it. When I don't want you to do it, you'll do it. Sorry, I'm talking to the computer. So, first in, first out is a reverse return. Okay, first in, last out is a direct return. Okay, so what happens is, so on this one, think about this. So let's dump 170 degree water here as an average. This one will dump 165 degree water. This point right here, we're coming back at 160 degree water, because let's say there's a 10 degree drop across this as it goes in. This one will get 170 degree water, but this one takes, let's make it 160 degree water there. So by the time it comes back here, this one's actually 155 degree water there. Okay, so we want to keep this balanced, but as we do that, the temperature is going to change. But it's also when we mix this, we're at 180 degree water. That's not right. Let's do that right. 180 degree water there. And ideally, we're going to be a mix of whatever. No, wrong place for that. Sorry. Forgot I got two systems in there. 180 degree Fahrenheit water there. All right, as this one drops, let's make this one 70s average. 160 is the average. That means when this comes back, this is 155 degree water here. Okay. With the system that we designed, we're going to come back here and be 180 coming in and mixing 155 here. Okay. And we're going to keep pushing 180, 155. So we literally have 25 degree. Zoom in on that a bit. So we have 25 degree temperature change between these two close coupled T's. Okay. Here we come down here. We're going to be 155 degrees Fahrenheit. As we come back here, we're going to be 160 degrees Fahrenheit. So literally here at this one, we literally have a 5 degree delta T, and let's do the delta T. So what we wind up with is by the time we get back here, we're literally 180 going around 160. So we'll get our 20 degree Fahrenheit delta T at the boiler, but yet it won't take us a whole lot to bring it back up. Whereas if we came back, say the secondary loop down here had 155 coming back, then we got to make up 25 degrees. So the more temperature we have to make up in the boiler, the more energy that's got to be put into the boiler. So if we can do a system that will get us a balanced temperature going back so we stay around 20 degrees, the better off it is. Now, are you ever going to get 20 degrees in the nose? No, you'll wind up with like 18.2. You'll wind up with 19. You'll wind up with 17. But that's why a reverse return is a better setup than a direct return, because inside the loop for the reverse return, we get to fix the water temperatures and get them back warmer. That makes sense? Okay. The other thing that goes with close couple T's, and we haven't really talked about pressure loss, but as you do this, we have less pressure loss between here and here than if we did a primary loop that was part of the heating system. So if we did boiler out and we started hitting fin tube, and it doesn't really matter how we do it, whether it's coming back in to a single direct return or if it's going to come back as a reverse return. When we start playing around with this, we got the pressure loss of the whole system. So we have a delta P based on the system losses. So that whole friction loss bit that you guys calculated last semester is what we're trying to avoid. So that's all coming back here as a large delta P here. I'm going to use an up arrow for large. Now I'm going to write it up. Delta P is large versus the close coupled up here, where our delta P when we come back to the boiler is smaller. Doesn't mean we don't have a pressure loss, but we just push fluid around X number of feet of pipe at what size and gone through how many fittings, it's going to have a pressure loss. But because we brought the fluid back in next to where we had a higher pressure, it's high pressure, high P here, and low P there, but we are able to keep these two delta P's being relatively small. Does that make sense?
Sure.
Okay, you say sure, but Fitz, do you get it?
Yeah.
Ian? Okay. So if you are literally thinking about this in terms of the pressure drop across the system, if you can come back in and you already have a high pressure there already, your delta P is less pressure, so therefore your pressure temperature relationship is going to be right. Okay. All right. That's probably not the really best description I've ever given a close coupled T's, but it'll work for the moment. Okay. Let's see if I can find you a better full definition of it. But okay, that's that. Now where are we at time-wise here? Cool, we're just there. All right. I posted some homework for you. It's up in there. I took some questions out of chapter 1 of Siegenthaler's book, so you can go back and read that chapter and find some of those answers. And then I gave you one on a diaphragm expansion tank for question number 8. I made it due Wednesday at midnight. It's got a drop box with it. You can ask questions on Wednesday related to it if you need to. Okay. Anybody got anything else? What? Say that again.
We have lab at 8 tomorrow.
Lab at 8 tomorrow?
Yeah.
That was the day, Dylan.
That was Monday. Yeah.
Oh, you just told me that.
Yeah.
Why?
So what you missed this morning in lab is I gave everybody a chance to ask questions about the lab project, and I went over a few things. I got a video I got to get posted out there, and I will after this class. Okay. Oh, the other thing I'm doing, I'm working on some HAP videos for you and Dr. Craig also. So I ran into a glitch. I made a mistake in some place, and I'm trying to fix it. So I'll get more of those done today. Okay. If not, I'll see you guys tomorrow around the building. Okay.
See you tomorrow.
I'll be there.
See y'all.
Me too. Asking about homework.